Welcome everyone to this presentation on ultrasonic biodiesel production. This cutting-edge technology, in use worldwide since the early 2000s, has transformed the production of biodiesel, offering a sustainable, clean-burning alternative for diesel engines. Before we delve into the advantages of ultrasonic mixing in biodiesel production, let's begin with a comprehensive overview of biodiesel and its manufacturing process. Biodiesel is a renewable fuel source from sustainable materials such as vegetable oils, animal fats, or waste cooking oils and greases. It possesses biodegradability and environmental friendliness, emitting fewer greenhouse gases compared to traditional diesel, contributing to a reduced carbon footprint. The primary raw materials for biodiesel production are triglycerides, found in vegetable oils or animal fats. These triglycerides contain fatty acids which serve as the foundation for biodiesel synthesis. During the transesterification process, triglycerides are converted into biodiesel, also known as methyl ester or ethyl ester, along with glycerol as a byproduct. This conversion involves breaking the ester bonds in triglycerides, replacing glycerol molecules with alcohol molecules, typically methanol, resulting in the formation of biodiesel molecules. Efficient mixing plays a pivotal role in biodiesel production for several reasons. Thorough mixing ensures all reactants come into contact, promoting faster and more complete reactions, preventing localized regions with varying concentrations and minimizing undesirable byproducts. Proper mixing enhances biodiesel yield and quality while reducing processing times, benefiting both small and large-scale facilities. With this understanding, we'll explore why ultrasonic mixing surpasses conventional methods such as impellers or blade mixers. Now, let's dive into the exciting part and explore the advantages of ultrasonic mixing in biodiesel production. Ultrasonic mixing offers numerous benefits compared to traditional techniques like blade mixers or stirrers. Most notably, it is significantly faster and more efficient. When comparing biodiesel production using ultrasonic mixing versus mechanical stirring, it's evident that ultrasound-assisted mixing boosts reaction rates within the heterogeneous oil and methanol mixture. For instance, using potassium hydroxide as a catalyst, Sonochemical reduced reaction time to just 5 minutes to achieve over 90% triglycerides conversion. In contrast, mechanical stirring yielded only about 80% conversion after 2 hours under the same conditions, which were molar ratio of 6:1 and a catalyst dosage of 0.5 weight percentage. In this slide, we see the comparison between mechanical and ultrasonic mixing and their resulting reaction times. The big difference between the two mixing techniques is clearly visible. Ultrasonic mixing achieves over 90% conversion yield in just 5 minutes, whereas mechanical stirring achieves only about 12% conversion. The superiority of ultrasonic biodiesel mixing is further highlighted by research conducted by Wu et al. In 2007, who observed that ultrasonic mixing resulted in dispersions with average droplet sizes 42% smaller than those achieved with standard impellers. This superior mixing promotes efficient mass transfer between phases, namely oil and methanol, enhancing biodiesel yield and product quality while consuming less energy compared to conventional methods. These advantages make ultrasonic biodiesel production not only versatile in accommodating various feedstocks, including low-grade oils and waste fats, but also reduce foaming, a common issue in traditional stirring methods. This in turn improves cost-effectiveness and process reliability. But enhanced mixing is not the only contribution ultrasound brings to biodiesel production. It introduces sonochemical energy, providing an initial boost to the conversion of triglycerides in oil. To better understand this, let's revisit the pathway from oil to biodiesel. Triglycerides, the primary fatty acids in oils used for biodiesel production, consist of 3 fatty acid chains attached to a glycerol molecule. To convert them into diglycerides, one of these fatty acid chains must be separated. This step is the bottleneck during the conversion of oil to biodiesel. The challenge here is that breaking the strong ester bond that binds the fatty acid chain to the glycerol molecule requires high activation energy. This means that this first reaction step, converting triglycerides into diglycerides, is energetically unfavorable and slow, requiring specific conditions such as high temperature, pressure, or additional catalyst. The efficiency and speed of this bond cleavage significantly slows the overall conversion rate down. This chemical conversion of triglycerides benefits drastically from sonochemical activation energy. Ultrasound cleaves first fatty acid chain with ease and efficiency so that the complete conversion from oil to biodiesel can be completed within a few minutes instead of several hours. So, how does an ultrasonic mixer produce these superior mixing and sonochemical effects? The unique principle of acoustic cavitation makes ultrasonic mixers highly effective. Acoustic or ultrasonic cavitation occurs when high-intensity ultrasound waves pass through a liquid, creating alternating high-pressure and low-pressure regions. During the low-pressure phase, small bubbles or voids form within the liquid, growing as pressure decreases further. When these bubbles reach a critical size, they collapse vigorously during the high-pressure phase, a phenomenon known as acoustic cavitation. Cavitation generates intense localized forces like shock waves, microjets, and high temperatures and pressures within the liquid. In this short clip, we demonstrate acoustic cavitation in action. You can observe the field of acoustic cavitation generated by a Hielscher ultrasonic probe inserted into a glass column filled with water illuminated by red light. The combination of mechanical forces, microscale liquid jets, and localized heating significantly enhances transesterification efficiency by promoting the mixing of oil, methanol, and catalyst. Due to these intense cavitational effects, ultrasonic mixing excels over alternative blending techniques, resulting in higher biodiesel yields, shorter processing times, and the ability to transform poor quality oils into high quality biodiesel. In ultrasonic biodiesel processing, ultrasonic reactors are utilized. Shown here are 3 different sonocators with power outputs of 500, 1000, and 1500 watts, each equipped with a flow cell reactor for continuous inline biodiesel production. In the flow cell reactor, an ultrasonic probe or sonotrode transmits ultrasound waves into the oil and methanol, transforming them into fine droplets. Flow reactors maintain a continuous flow of reactants, ensuring consistent and uniform reaction conditions, eliminating issues related to concentration gradients and temperature fluctuations that can affect batch processes. Since ultrasonic mixing for improved biodiesel transesterification is performed in a flow cell reactor, the mixing effect of ultrasound is concealed behind the reactor's stainless steel walls. To illustrate the mixing power of a probe-type sonocator, we demonstrate its capability in a glass beaker. In the video, we mix oil into water, which, like oil and methanol, are immiscible. In the flow cell, oil and methanol are fed directly into the cavitation hotspot. To achieve the same effect, we inject oil with an eyedropper into the cavitational hotspot beneath the sonotrode head. As you can see, sonication blends the water and oil rapidly within seconds into a homogeneous water-oil mixture, so that a maximum contact between both phases is achieved. Therefore, when oil, methanol, and catalyst are mixed with sonication, the transesterification reaction goes rapidly and turns the triglycerides into fatty acid methyl ester, aka biodiesel and glycerin. If you're still not convinced why you should opt for an ultrasonic mixer, let's compare ultrasonic mixers with mechanical stirrers to assess differences in mixing performance and efficiency. We've already seen that ultrasonic mixing reactors produce higher yields of biodiesel within a very short process. This advantage of increased biodiesel yield by ultrasonic mixing becomes even more pronounced when lower quality oil is used as feedstock. The numbers clearly demonstrate the superior efficiency and performance of ultrasonic mixing for biodiesel processing. This is because ultrasound produces nanodroplets and increases the reaction rates inside heterogeneous mixtures. Combined with the energy efficiency of the production process and compatibility with any catalysts, sonication delivers outstanding results in biodiesel production. Furthermore, ultrasonicators are a very energy-efficient method of blending, contributing to the overall efficiency of ultrasonic biodiesel manufacturing. When compared to other conventional mixing techniques applied for biodiesel production, ultrasonic reactors excel with lower specific energy consumption. Since energy is a major cost factor in biodiesel processing, the use of ultrasound for biodiesel production helps significantly to make your biofuel production profitable and environmental friendly. Besides high yields, a quick reaction rate, and energy efficiency, the obtained biodiesel quality is important too. ASTM standards with ultrasonically produced biodiesel. Wood et al., 2013, produced biodiesel using the Hielscher 500-watt Sonochemical model UIP 500HD in a continuous flow setup. To compare the quality of the ultrasonic biodiesel with the stirrer-produced biodiesel, they examined the obtained biodiesels using a 27/3 test. This test shows how thoroughly the methanol and waste vegetable oil have reacted with each other. It is done by mixing 3 parts biodiesel and 27 parts methanol. When mixed together, the solution should have a single-phase clear look, signifying a pass. However, if the solution is cloudy and has more than one phase, the biodiesel needs to be reacted again. This test correlates well with ASTM qualities and is quite equivalent to ASTM D6584. In the picture, you can see the test tube with the ultrasonically produced biodiesel, which is completely clear and shows no sedimented phase. On the right side is the test conventionally produced biodiesel, which is cloudy and has 2 phases. By the 27/3 test performed by Wood et al., it is demonstrated that ultrasonically synthesized biodiesel has better quality and fulfills ASTM standards. From small to big, with Hielscher ultrasonic mixers, you can start your biodiesel processing at a small or mid-size production plan. Whether you're a small-scale biodiesel producer with 80 gallons per hour or a mass producer of tens of thousands of gallons per hour, Hielscher Ultrasonics offers the optimal sonicator for your transesterification. Biodiesel mixers from Hielscher are available at any size and for any required flow rate. Whenever you want to produce higher throughputs of biodiesel, you can easily scale up your ultrasonic mixing process by simply adding additional sonicators and operating them in parallel. This allows you to adjust your production goal depending on current demands for biodiesel, investment, and overall production and distribution capacity. This is especially helpful for small businesses and startups. With the environment and sustainability in mind, it is another benefit that ultrasonic biodiesel mixers contribute to sustainability and are part of an environmental-friendly biodiesel production. Ultrasonic biodiesel production uses fewer chemicals, generates less wastewater, and has a reduced carbon footprint, all contributing to a greener and more sustainable future. At this point, we want to underline the advantages of ultrasonic biodiesel manufacturing with science-based data. Let's dive into scientific studies to see how the advantages of sonication turn out when investigated by researchers. We'll begin with a study titled Single-Stage Waste Oil Conversion into Biodiesel via Sonochemical Activation over Bio-Based Biofunctional Catalyst, Optimization, Preliminary Technoeconomic and Environmental Analysis by Naeem et al. From 2023. The research team used the Hielscher Sonocator UP200HT to investigate the potential of promoting single-stage biodiesel transesterification of waste oil catalyzed by potassium hydroxide and corncob activated carbon. To obtain data for evaluating industrial biodiesel production, they used the Sonocator model UIP 1500HDT. The research team reports outstanding results. Using poor quality oil, they achieved a biodiesel yield of 88% within a very short reaction time of just 5 minutes. This means that the transesterification process was completed rapidly and with a high turnover. Additionally, it is important to emphasize that the generation of soap, an undesired side product during biodiesel manufacturing, was avoided. The ultrasonically produced biodiesel was of very high quality, fulfilling ASTM standards. In comparison to other blending techniques, ultrasound-assisted catalyzed biodiesel mixing is considered preferable due to the rapid conversion, allowing for high throughputs and excellent biodiesel yield. But not only is the quality of biodiesel superior, the economic and environmental numbers for ultrasonic biodiesel processing excel too when compared with conventional stirring methods. The study calculated that the production cost for ultrasonically produced biodiesel was 0.776 cents per liter of biodiesel, with a return on investment found to be 334%, and total emissions of 0.08 kilograms of CO2 of biodiesel. Overall, the study demonstrated a highly efficient and cost-effective biodiesel production process using waste oil as the feedstock. The process achieved a high biodiesel yield, met quality standards, had a short reaction time, and showed a substantial return on investment while maintaining environmental sustainability with low emissions. These findings highlight the advantages of ultrasonic mixing for the biodiesel manufacturing industry and demonstrate the potential for improving production processes and economic outcomes. Another scientific study focused on the economic comparison of stirrer versus ultrasonic biodiesel production. Gholami et al. Published in 2021 a study titled Technoeconomic Assessment of Biodiesel Production from Canola Oil Through Ultrasonic Cavitation. In this groundbreaking study, the researchers set out to investigate the key cost drivers in biodiesel production. Traditionally, these costs have been associated with purchasing oil, energy consumption, post-processing steps, and equipment maintenance. However, what Gholami and their team discovered was nothing short of revolutionary. They compared two biodiesel production methods, one using conventional mechanical stirring and the other harnessing the power of ultrasonic cavitation. The results were eye-opening. The ultrasonic biodiesel reactors emerged as greatly cost-saving in this story. Here's how. First, ultrasonic cavitation reactors enable the use of cheaper oils, which can be converted almost entirely. This reduces the reliance on costly feedstocks. Second, they boast remarkably low energy consumption. The sonocators work with minimal energy requirements, eliminating the need for extensive heating. Third, less methanol and catalyst are needed in the ultrasonic process, further slashing costs. The energy efficiency gains don't stop there. In a head-to-head comparison with mechanical stirring, the ultrasonic process significantly reduced energy consumption during methanol recovery and biodiesel purification by 26.5% and 1.3% respectively. This reduction can be attributed to the lower quantities of methanol entering the distillation columns in the ultrasonic process. But the advantages of ultrasonic cavitation don't end with energy savings. The ultrasonic cavitation reactor also has a remarkable impact on material requirements, lowering energy consumption to nearly 1/3 of that required by a stirred tank reactor and reducing methanol and catalyst consumption by 25%. From an economic standpoint, the ultrasonic cavitation process presents clear advantages. It boasts lower total investment costs thanks to a nearly 50% reduction in reactor costs and an 11.6% drop in methanol distillation column costs. Furthermore, the ultrasonic cavitation process reduces the overall biodiesel production cost, thanks to a 4% reduction in canola oil consumption, lower total investment, 2.2% less chemical usage, and a 23.8% decrease in utility requirements. The story of ultrasonic cavitation continues to shine in terms of economics. Unlike the mechanical stirring process, the ultrasonic cavitation process offers a positive net present value, shorter payback time, and a higher internal rate of return, making it an attractive investment choice. The benefits of ultrasonic cavitation extend beyond the economic realm. This process is a champion for the environment, resulting in an astounding 80% reduction in waste streams. This reduction is primarily due to higher conversion rates within the reactor and reduced alcohol consumption during the process. In conclusion, the study of Gholami and his colleagues paint a compelling picture of the ultrasonic cavitation process as a game changer in biodiesel production. And switching to ultrasonic biodiesel production is easy as well. Even for existing biodiesel producers, changing from traditional blade stirrers or impellers to an ultrasonic mixer is straightforward. Since all Hielscher sonocators are compact with a small footprint, they can be easily installed and retrofitted into existing biodiesel plants. Installation, operation, and maintenance are hassle-free. For installation, no specifically trained specialist is required. Depending on the sonocator size, an electrician or facility operator can install the ultrasonic mixer within a few hours. For operation, no specific training or education is needed. However, Hielscher ultrasonic experts are glad to assist you with in-depth know-how during installation, first runs, and further process optimization tips. The maintenance of Hielscher ultrasonicators for biodiesel is negligible. In general, the ultrasonic mixer will run for years without major maintenance needed. Would you like to take ultrasonic biodiesel mixing to its limits? With the Multiphase cavitator, a unique flow cell insert patented by Hielscher, your biodiesel production becomes even more efficient. This ultrasonic insert is equipped with 48 exceptionally fine cannulas, delicately injecting the dispersed phase into the continuous phase precisely within the cavitation zone. The result? The creation of minuscule suspended droplets of the dispersed phase in the continuous phase, leading to an extraordinarily high specific surface area. In the context of ultrasonic biodiesel production, the multiphase cavitator continuously introduces the methanol catalyst phase into the oil stream, revolutionizing the way we approach this critical process. Designed to seamlessly integrate with Hielscher flow cell reactors, it offers the flexibility of both batch and continuous processing. What sets this innovation apart is its approach to combining different phases. Unlike traditional methods where separate phases are merged before entering the flow cell and encountering cavitation, this ingenious flow cell insert excels at harmonizing these phases. As liquid is gently introduced through the 48 fine cannulas, it enters the flow cell in exquisitely narrow strands. High-power ultrasound meticulously slices the incoming liquid strands into minute droplets as they merge with the liquid phase within the flow cell. The exceptional performance enhancement of ultrasonic emulsification is due to the multiphase cavitator's ability to apply uniform feed pressure from a single supply to all 48 cannulas, ensuring a harmonious and consistent flow among them. To conclude, ultrasonic mixing in biodiesel production offers a wave of advantages, from faster and efficient reactions, higher yield, and improved product quality to energy savings, scalability, and environmental friendliness. This innovative technology opens new doors for the biodiesel industry, promising a more sustainable and cleaner future for all. Now that you have a comprehensive understanding of ultrasonic biodiesel technology, we encourage you to take the next step in exploring Hielscher sonicators for superior biodiesel transesterification. If you have any questions, please don't hesitate to contact us. Our experts are here to provide in-depth knowledge about ultrasonic biodiesel processing and ensure that you have all the necessary data to make informed decisions. Additionally, our staff is eager to engage with you on a deeper level. Schedule a meeting or call to discuss your specific application, challenges, and goals. Our experts will work closely with you to understand your unique requirements and provide personalized recommendations and solutions for highly efficient biodiesel production. Our team will propose the most suitable sonicator for your biodiesel production goals, provide you with detailed pricing information, and tailored proposals. Don't hesitate to reach out. We look forward to hearing from you and are eager to work with you towards your success. If you found this presentation informative, please give it a thumbs up. And if you wish to stay updated on our future videos, please subscribe to our YouTube channel. Thanks for watching.